The operational definition of velocity is very simple once we've operationally defined displacement. All we have to do is take our operational definition of displacement, delta r, and divide it by how many seconds on our Mickey it took to make that displacement. Now it turns out that we have three flavors of velocity: uniform, average, and instantaneous. And I hope today to be able to talk about all three of those flavors. Now folks, I'm waiting for Friday. Okay? On Friday, all of you will have been through that first tutorial when Don geht's los. Then I'm just going to take off. We're going to build on that experience. But today I'm just kind of treading water to get us to Friday. Okay, let's talk about uniform velocity. Uniform velocity looks like that. And let's talk about graphing uniform velocity. Now folks, my experience has been that many of you, you look at a velocity versus time graph or a position versus time graph, and it just speaks to your soul. They just talk to you. Others of you are scared to death of them. And so I apologize to those of you that already can do this. We're going to just try to help the rest of the class, okay? You want to see a graph as a collection of data points. If I'm plotting position versus time, and time will always be the horizontal axis on these motion graphs, what I want to do is I want to look for data points. At t equals 0, the cart or the truck is at position 0. So I put a data point. At time equals 0, it's at position 0. And then I wait 15 seconds and it's gone 60 centimeters. So I go out 15 seconds, I go up 60 centimeters, I put a point. I hope you're bored. I then wait 15 more seconds, I do it again. When I connect the dots, I'm being arrogant. What I'm saying by connecting the dots is that if I wanted to, if I had no social life at all, I could have collected 1,000,000 data points. And if I had put all 1,000,000 of those data points on there with red ink, they would have blurred together into that line. So whenever you see a motion graph, you want to see the red line as a bunch of red dots that are smeared together. Each red dot being a data point. So like right here, at t equals 10 seconds, I would be at 40 centimeters. A bunch of data points. Again, everyone, most everyone already knows that. What if I just give you that plot and I ask you, what's the velocity of the truck? How would you get it from that plot? The slope of the line. Yeah, you just take the slope of the line, which is just the rise over the run. Now, in order to take the slope, you have to have two data points. You pick any 2 points on the line, and you compute the rise. In this case, it would be 100 minus 40, or 60. You compute the run. In this case, it would be 25 minus 10, or 15. You divide the rise by the run, and you get the slope. In this case, it would be 4 centimeters for each second. Now, we're going to do something completely different. I'm going to look around the room, and I'm going to find everything I can that is circular. Everything that I find, I'm going to measure the circumference and the radius. And I'm going to do this with all sorts of objects. I will then plot them on a graph, where the vertical axis is circumference, the horizontal one is radius. I find to my delight that all of my objects in the room that are circular lie on a single straight line graph, where the slope of that graph is 2 pi, 6.28, 6 and change. What does that slope tell you about circles? What does 6.28 tell you about circles? Talk to your neighbor, please. Before I let you answer that, we're going to do a little thought experiment. Suppose that I go down to the hardware store, Ace Hardware, and I buy a lot of red rope, and I tie that snugly around the earth. Now, to make this a little simpler, let's suppose that the earth is perfectly spherical, and that the seas are frozen so that it doesn't, get soggy and sink to the bottom of the ocean. So this is snugged up around the earth, and then I go back to the hardware store and I buy an extra 20 feet of rope. I splice that extra 20 feet in, and all the people of the world stand shoulder to shoulder along the rope. We all bend down and we lift together the same amount. So everywhere around the earth, this rope is the same distance above the ground. Now, what's the smallest thing that could fit under this rope? Would it be an amoeba, a bumblebee, a cat, or a dinosaur? With your clicker, people. What is the smallest thing that could fit under this rope?
An extra 20 feet.
Yeah. Not at all.
We add 20 feet of rope, splice it in, and we all lift the same amount. We are the world. We are the children. Okay? Last call. Okay, an amoeba. Wait a minute. I don't usually do this. But with the 10 people that said a dinosaur, please raise your hand. Okay, folks. We have to decide. Are we going to let them stay in the class if they're not going to take it seriously?
What about
You're right.
The answer, people, is a dinosaur. Yes, those 10 people got it right. And the rest of you are wondering, how can that be? 20 feet is negligible compared to the distance around the earth. It's got to be an amoeba. It can't be a dinosaur. It's a dinosaur. And the answer is tied up with the interpretation of this slope. The slope of that line is 6 pi. That means if I want to increase the radius of any circle, whether it's a big circle, small circle, any circle, if I want to increase the radius of that circle by 1 unit, let's say 1 foot, I have to increase my circumference by 6.28 feet. That means if I want to raise this rope up off the ground 1 foot, I have to add 6.28 feet of rope. Now 20 is 3 times 6 for large values of 6. So that means that when we add 20 feet of rope, we're going to be able to lift that rope 3 feet. And that's big enough for a dinosaur to get under. Not that kind of dinosaur. I'm talking about the one that got the fellow in the Jeep. You remember? That was a scary movie. I let my youngest son watch that when he was too young. It terrified him. Okay. Now, folks, here's the point. The slope is where all the science is. The slope is telling you how much change you have in this axis for every 1 unit change in the horizontal axis. 4 meters down or 4 centimeters down the road for every 1 second that ticks by. Now science in general, and physics in particular, is all about finding relationships between different variables. And when you find a straight line relationship between 2 variables, the next thing you're going to do is find that slope, because that's where the Nobel Prize is. Okay? That's where the science is hidden.